Welcome back, everybody. Mr. Johnson again here with you. It's still Sunday, September 20th. We are on section 3.3, page 126 of our ebook. And this is a continuation of the conversation about mole conversions. 3.3 is titled The Wheel Model of Mole Conversions. And the reason why, and I'll show you in a moment, is that our book uses a wheel as a graphic representation of how we can convert between a variety of other quantities and the mole, or from a variety of one quantity to another. This first highlighted section in our book says that a quantity of a substance can only be related to another quantity of the same substance through the mole. If you've been wondering why we're doing this, what's the big deal? Well, mole conversions, using the mole concept, which you heard me say earlier is terribly fundamental, is how we are able to calculate and determine all sorts of things in chemistry that are interesting. For example, if we want a certain amount of energy out of a combustion reaction, we've got that outcome in mind, a certain number of kilojoules we want. We could figure out how many grams or moles of a certain substance are needed to burn in the presence of oxygen to produce that much energy. Or if we've got a certain amount of a fuel or an explosive, we could figure out how much energy is going to come out of that. We want to make a certain amount of a substance, a certain number of grams of a substance, and it comes from a chemical reaction. We use mole conversions to figure out how many grams or liters, if it's a liquid, of each of those substances are needed to make the desired product. So keep in mind that there is great relevance to what we're doing, and that the majority of the problems we're going to solve all year will involve mole conversions and a skill called stoichiometry, which we're working our way toward. So I've just scrolled down, and we're now looking at this wheel model. And at the center of it is the mole, because at the center of chemistry, at the center of stoichiometry is the mole. And what this is telling us is that if we, for example, want to go from the mass in grams of a substance to the number of atoms, if it were an element, or the number of molecules, if it were a compound, we'd have to go through the mole to do so. There's no direct conversion from mass to a particular number of items. Got to go through mole. Now you could create one. You could create a conversion factor that takes you there, but it's accounting for that within that you're going from mass to moles, and then from moles to items. Or, if you're starting with items, from items to moles, and then moles to mass. It's also reminding us that when we go between mass and moles, we use molar mass. And that when we go between moles and a number of atoms, we use Avogadro's number, or 6.02 times 10 to the 23. So what we're about to do is a two-step problem where we either go from grams to the number of items through moles, or from the number of items to grams through moles. I've flipped my page. I'm now on 127 of the ebook. I'm not going to solve the sample problem with you, but you might take a look at it if you want to gain a little bit more insight into how this works before I do a problem with you. But this one's starting with grams, 5 grams of copper, and we're trying to get to atoms, and the little solution here is saying that, well, first we go from grams to moles using molar mass, and then we go from moles to atoms using Avogadro's number. If we scroll down in the next problem, it's going the other way. We're starting with an atom and going to grams. And in that case, use Avogadro's number to get to moles, and then molar mass to get to mass. So I'm going to flip my page and do a problem with you. All right, so I've flipped my page. I'm now on 128 of the ebook, and I'm looking at practice problem 2 here at the top of that page. How many atoms are in 2.1 grams of bromine? All right, so let's acknowledge that we cannot go directly from grams to atoms. We've got to go through the mole first. So we're going to go from the mass in grams of bromine to moles of bromine using Avogadro's number, and then we'll go from moles of bromine to atoms. I misspoke. We're going to go from grams of bromine to moles using molar mass, and then we will go from moles to atoms using Avogadro's number. So I've written 2.1 grams of bromine, once again in the upper left-hand corner of my first DA box. I like to put a 1 down there so I know not to write anything else. And again, to go from grams to moles, I'm going to use molar mass. With grams up here, I know that I need grams on the bottom. So I'm going to look at my book real quick because I forgot bromine's molar mass. And it is 79.90 grams per mole. So I put 1 mole of bromine on the top and 79.90 grams of bromine on the bottom. And at this point, I keep going. I don't go to my calculator and figure out how many moles that is, and then set up another problem with the answer from the first as the beginning part of the second one and go to atoms. I do it all at once. This is a 2-step dimensional analysis problem. But at this point, grams have canceled, and I've got moles of bromine. So I now want to go from moles to atoms. I know that with the unit moles up here, I've got to put 1 mole on the bottom, and 1 mole is always equivalent to 6.022 times 10 to the 23, atoms. And when I go to my calculator, I get 1.58275. I want to remind everybody once again that when you're entering numbers in scientific notation in your calculator, don't hit the times button there. Use your EE or EXP button. Fewer mistakes will be made that way. So I need to round to, it looks like 2 significant figures because 2.1 has the fewest. So this is going to be 1.6 times 10 to the 22. I neglected to say that my calculator had times to the 10 to the 22 here. Times 10 to the 22 atoms of bromine. 1.6 times 10 to the 22 atoms of bromine is my final answer. I'm going to do one more with you, but if you feel like you've got the hang of this and want to move ahead, feel free to skip this section, but I am going to do practice problem 3 on this same page. So it's asking us, what is the mass in grams of 1 atom of silver? And we should acknowledge that a single atom of silver, we know the mass of in AMUs off our periodic table. It's 107.87 AMUs, but we're wanting to find it in grams. And it should be a pretty small number. The mass of a single atom in grams should be pretty darn small. So I'm going to go from atoms of silver to moles, because I've always got to go to moles first, and then from moles of silver to mass. To go from atoms to moles, I know I use Avogadro's number, so I put 1 mole of silver on top, and 6.022 times 10 to the 23 atoms on bottom. Atoms have canceled. Now I want to go from moles of silver to mass, so I need to put 1 mole of silver on the bottom, and the molar mass of silver on the top, which is 107.87 grams of silver. That last step cancels moles, leaving me with the unit grams, and my unrounded answer from my calculator is 1.79126. 1.79126 times, not going to forget it this time, 10 to the negative 22 grams of silver. That's a G. But I need to round to 4, not 5 sig figs. The idea being that the 1 is exact. In exactly 1 atom of silver, approximately how many grams are there? There will be times when Avogadro's number, this coefficient, 6.022, has the fewest sig figs in a problem and can limit sig figs. In fact, conversion factors can do that, and other times they won't, and I'll talk with you when they won't. So this is going to be 1.79, that 1 stays a 1 because the 2's not a 5 or higher, 1.791 times 10 to the negative 22 grams of silver. And that's the answer to practice problem 3. All right, so I'm on the same page now, still on page 128. I've scrolled down a little bit, and we're in this section that says two-wheel conversions. So we're going to, for the first time, get into a little bit of stoichiometry. But the more traditional type of stoichiometry is going to come to us actually in a couple more weeks. So our book says that stoichiometry is the branch of chemistry that deals with the quantitative relationships between elements in a compound and between the reactants and products in a chemical reaction. And how we use it most often is to, if we know the mass, for example, of a reactant, using stoichiometry, we could figure out the mass of one or both products, or maybe the volume if one is a gas. As I mentioned a bit ago, we could also use stoichiometry if we knew the mass of a fuel to figure out how much energy in kilojoules would come out of that reaction. The graphic here is showing the two-wheel or stoichiometry graphic, and we're not going to actually use that in this lecture. I'll be showing you it and how we use it in a little bit, actually in a couple of weeks. But I do want to mention this, which says that a quantity of a substance or species can only be related to a quantity of another substance or species through the mole. Once again, everything goes through the mole. Anytime we want to go from the amount of one substance in a chemical reaction to the amount of anything else, we have to go through the mole to do so. All right, so we're looking at this chart now at the bottom of that same page, 128 in our ebook. And I'll go to the second row. We'll use the example because I think it'll make more sense with an example. And what this chart is telling us is that from a formula like CO2, we are able to determine the ratio of atoms to one another in that compound, which can be thought of as a mole ratio because everything can be scaled up through Avogadro's number to a mole. And that ratio can be written as a conversion factor. So in CO2, with one C and two O's, that's saying that in one molecule of CO2, there's 2 atoms of oxygen. No, 2 atoms of oxygen are not equal to a molecule of CO2, but in terms of the formula, in terms of a CO2 molecule, in that context, yeah, there's 2 atoms of O for every CO2. We could also say that one molecule of CO2 equals, or is equivalent, in the context of CO2, to 1 atom of carbon. Well, again, we can scale that up to a mole using Avogadro's number and say that in a mole of CO2, there's 2 moles of O atoms. And we always really think about those equalities or ratios in moles, because at an atom level, it's just too small to really contemplate or to be useful. So in a mole of CO2, there's 2 moles of O, or we could also say in a mole of CO2, there's 1 mole of carbon. Well, all equivalencies can be written as conversion factors, as fractions. So we see over here that 1 mole of CO2 is equivalent to 2 moles of O, again in this context of CO2, or it could be written as its reciprocal, where we say 2 moles of oxygen atoms are equivalent in this context to 1 mole of CO2. In both these cases, we could have had 1 mole of C on the bottom here, because there's 1 C for CO2, and we could have had, if we wanted to, 1 mole of C up here. It just chose to use oxygen as the example. I'm now on page 130 of the ebook, and I want to acknowledge that I skipped a couple of sample problems. If you want to go back and look at those to help build your understanding a bit better before we solve this together, I recommend doing so. Otherwise, sit back, relax, and enjoy a bit more dimensional analysis. So we've got how many moles of KNO3 contain 14 grams of oxygen. So I've plotted out my route up top. I know that in 14 grams, I know that I'm going to go from grams of oxygen to moles of oxygen. And then from moles of oxygen, I'll go to moles of KNO3 using the formula. Grams to moles using molar mass, and then moles to moles using the mole ratio or the formula for KNO3. With grams up top, I need to put grams on the bottom, so I'm going to put the molar mass of oxygen on the bottom. That's 16.00 grams in 1 mole of oxygen. Let's acknowledge this is oxygen atoms, not molecular oxygen, which is always O2, which would have a molar mass of 32. So grams have canceled. And now, using the formula of KNO3, I want to go from moles of oxygen to moles of KNO3. Well, there's 3 oxygens in KNO3. The ratio, the mole ratio of oxygen to KNO3 is 3 moles of oxygen for 1 entire KNO3. So I'm going to put 3 moles of oxygen on the bottom, again coming from the subscript, and that's so that moles of oxygen cancels, and I'll put 1 mole of KNO3 on the top. Being left with moles of KNO3, what I wanted for my answer. And when I plug this into my calculator, I get 0.2916 repeating moles of KNO3. Once again, I'm going to round to sig figs. This ratio is exact. In exactly 1 mole of KNO3, there's exactly 3 moles of oxygen, so those won't limit sig figs. Got 2 sig figs here, 4 here, 1 mole again being exact, so I've got to round this to 2 sig figs, which is going to be 0.29 moles KNO3. And that's it, folks. Enjoy yourselves with whatever it is you're going to do next, and I'll see you for the next lecture in just a little bit.